We need to talk about ways of writing programs that use loops but have more than one variable. In all of our previous examples, all we've been doing is working with this one variable that counts. That's the counter that we use to actuate our loop. So we count from 1 to 5 or 10 to 15. And then in each step, we just do something with the counter. So I'd print out, 2 squared is 4, 3 squared is 9. What I want to do with this exercise is talk about what if our program has to do something that involves counting, like counting from 1 to 6, but also needs to store some second thing on the side. So the task is to compute this sum. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. And the prompt is concrete. It says go from 1 to 6, but design the code in such a way that it would be really easy to make it do 1 up to 1,000, not just 1 up to 6. Because otherwise, of course, you could just do this by hand. You could just compute the sum on the side with a calculator and then put that in the program. I want to use a loop for this. Exam questions, of course, will typically be a lot more specific. They won't say you have to use a loop. They just won't give you a problem that you can solve by what we would call hard coding the answer. You can't just put the finished number in there. You have to be computing the number. You might also notice, this will be something we come back to in a minute, but it does say the finished program must output only that final sum. Just one number at the end, and that's it. So not a bunch of other extra data. On programming assignments and things, if you are told in the assignment you must output something in exactly this format, then we're not kidding. You must make sure before you hand it in that the format is exactly the same as what we expect. And that's significant. And unfortunately, early in this course, people often lose lots of marks because they don't believe us when we say that. We mean exactly. In an engineering or scientific setting, exact means exact. We need to enforce that level of rigor, and it's important also for fairness because we know that there are some types of extra output that we just couldn't read at all. And because we want to make sure we treat everybody fairly, the only truly fair rule here is to make sure everybody has to follow the exact same rules. So that's one thing. But notice that it says the finished program. Obviously, while we're developing it, we're free to have extra output to make sure we understand what's going on. But it's really important that we remove all of that extra stuff before we produce the finished program. So the question then is, how do we start tackling a problem like this? And I sort of like designing this kind of solution from the outside in. So I know that, okay, that's very nice. It pasted that for us, just to remind us in case we'd forgotten. I know that I'm going to want to print out a sum at the end. So why don't I make a variable for it? Int the sum equals 0, and then somewhere at the end I will print out the sum is, and then this, the sum. And I'm even going to compile and run that just to make sure that I've got my printf working. Usually when you sit down to do programming, you get a bit superstitious that you've forgotten everything. So it's good to verify that you remember basic stuff like how to write print statements. I also will add that, of course, it says here you must output only the final sum. On assignments, it won't just say that. It'll say the output must look exactly like this. So you wouldn't even have any choice in like what it prints before it prints out the sum. You might be told just print the number and nothing else. But for this exercise, because it's just me hollering at a video, I can bend the rules a little bit. So I know that I have a variable called the sum, and eventually I print it out. And then the question is, how do I get it to contain what I want? And of course, you could think about it like, well, hey, I just could compute the sum by writing the sum equals 1 times 1 plus 2 times 2 plus. But think about it, that if you do that, then it's not very flexible. If you want to modify it to go up to 15 or 1,000, you just have to make one massive line here. Instead, what I want to do is come up with something that lets me break it up into small pieces with the goal of eventually using a loop. And just to justify that a bit more, so I want to compute the sum 1 squared plus 2 squared plus 3 squared plus, and then some more stuff up to some point. I think the way I want to do this is I'm going to compute each square separately. Compute 1 squared, and then I'm going to add that into my sum. Then I'm going to compute 2 squared and add that into my sum. That lets me break this up into a bunch of bite-sized pieces. So the way I'll do that here is I'll start with the sum equal to 0, and then I'll say, okay, at each step, the sum equals the current sum plus the next square in the chain. So there's the sum plus 1 times 1, and then I'll just copy and paste that. And remember that this is our goal when we design loops. The best way to hack away at a loop problem is create code without a loop that you can copy and paste, and then sort of reverse engineer that into a loop. Okay, so I'm going to paste it 6 times. There's plus 2 times 2 plus 3 times 3. And the reason I like this development style is that because we start with such basic things, it's much easier to verify that what we're doing is correct at each step. Okay, so I'll save that. And of course, we need to make some changes to this, but it gives us somewhere to start from. And it says the sum is 91. And you could work out on paper what the sum actually is, or you could also test out your logic on a smaller sum. So what's the sum of 1 squared plus 2 squared? Well, I'd expect that to be 1 plus 4, or 5. So we'll just make sure that my logic is holding up. Okay, that looks good. So I've empirically validated that my code seems to make some sense. And then I think, okay, I now have a process that'll get me to the right answer, but I need to make it more flexible so I could go up to 1,000 or 1,000,000 or something. So how can I automate this further? And I notice, well, hey, wait a minute. 1 times 1, 2 times 2, 1, 2, 3, 4. It looks like I'm counting. Why don't I use a variable to represent the square that I'm currently working on? And I'll call that variable, in the absence of any better ideas, I'll call it I. So I'll say, okay, at each step I do the sum equals the current sum plus the square of the next number. And then I equals 1 at first, so at each step I add 1 to I. So this is adding in 1 times 1, and then it sets I to be 2 afterwards, and I can keep working. And you might already see what's about to happen here. I now have a piece of code that I can literally copy and paste. So I've got I equals 1, and the sum equals the sum plus 1 times 1, and then I set I to be equal to 2. Now if I do it again, I get the sum equals the current sum plus 2 times 2, and then I set I to be 3, and then 4, and then 5, and then 6. Let me just make sure I've counted that off correctly. Oh, one more. Okay, so I'll save that. We'll take a look at it. And the sum is 91. That is the answer I expect. And notice that the code that I have here is literally identical at each step. In other words, it looks a lot like a loop body. And so I could turn this into a loop. And remember that the key thing here is that my incrementation condition, the way that I make progress at each step, is by counting up with the variable I. I do use this variable, but it isn't relevant to how long the loop runs. The loop is going to keep running from 1 up to 6 in terms of the value of I. And then up here I've got my initialization. So I think what I'll do is I'll just clean these up away because we don't need them anymore. And I will stick a loop body around the outside of this. So while I is less than or equal to 6, and to me it's natural to use a while loop for this because I already have the incrementation buried in here. And so all I need to do is to insert that continuation condition and then wrap everything up inside a while loop and then of course indent it. Each time you go inside a set of curly brackets, you should indent the contents by one more layer. We'll see shortly that you can actually have multiple layers of curly brackets. You in fact could have a while loop inside of a while loop. And if that happens, you'll want to indent the contents of the inside loop even further. But for now, we just have this. So I'll try this out. So notice the process I use. First, I tried to perform the computation by hand. Then I tried to do it, breaking it up into line by line into smaller pieces. Then I tried to automate that so that it was actually literally the same code copied and pasted. Once I had that down, I could condense it down into a loop body and then stick it inside that while statement. So we'll try this out. And we can see there it is, the sum is 91. And then just at the end, so I want to demonstrate first that I could compute now the sum of squares from 1 up to 100, or from, let's say, 5 up to 100. Because, of course, now that I have a loop that works, I can modify the parameters as I see fit. And maybe you could say, well, wait, you don't know that the loop actually works yet. Maybe you just got lucky. And that's a good point. So let's try going up to 2. And we'll do the same experiment we did before. We know the sum should be 5 if I only go up to 2. And sure enough, there it is. The sum is 5. So I could validate this further, but I think it's reasonable to suggest that the loop is likely working correctly. So I now have a while loop that does this. We'll run that again to make sure we're back to where we were a minute ago. And I actually, just at the end here, I would like to package this up into a for loop as well. So there's the while loop version. And we'll just put a comment around that. And let's now write the for loop version. Okay. So in my for loop, I get to put the initialization and the continuation and incrementation on one line. And so I can write int I equals 1. Notice that I am actually allowed to declare my loop counter inside the for statement. That's a nice convenience because obviously I often use variables to count inside of loops. So I can just put the declaration right inside there. And we'll see I think in the next video, we're going to begin talking about something called scope, and that's relevant to how long a variable lives in the program. And it turns out that by putting this here, we do change the lifespan of the variable, but that'll come up again later. For now, I think it's a great convenience. Okay, so for I equals 1, I less than or equal to 6, I equals I plus 1. Or I could write I plus plus, or I could write I plus equals 1. And at each step, I write the sum equals the sum plus I times I. And notice that in this loop, I'm not using this variable, the sum, inside of any of my 3 ingredients, because the loop is governed by the variable I. We'll try that out. The sum is 91. Now, what if you got to this? What if you got to a while loop or a for loop and something wasn't working properly? The sum wasn't coming out correctly, or maybe the loop was infinite. One thing you could try, because you might notice if you get an infinite loop in this situation, so what if I write I starts at 1 and then I forget to increment I. So I is going to stay at 1 forever because I just add 0 to it. This is going to result in an infinite loop. And you can maybe verify that. You might want to try tracing through that by hand to see what happens. But if I run this, you might notice it just sits there and does nothing because it's trapped inside this loop around line 28. And you can see there's no print statements, so it has no reason to tell us anything. It just sits there and does nothing. We don't know what's going on. Is the program just taking a long time? Will it ever finish? And that's a question we don't know the answer, but once we get impatient, we press Control-C, and that ends the program, that forcibly ends the program. And then we go and try and debug this. So one thing I recommend is, obviously when we're done, we have to have only this one bit of output. But when you're debugging or when you're testing, it's fine to add extra output. I might actually do this in the loop to make sure my loop is working. I'm going to write, okay, in the loop, the sum is this and I is this. A lot of people, when they write little print statements for debugging reasons, they don't put some text in it. They just put %d. You'd be surprised. I know it seems like a waste of time to write the text. I find that it's easier for me to debug if I write a complete sentence in here, or at least some point, like something that identifies what print statement I'm dealing with, so that it's easier for me to put the pieces back together in my head if something is misbehaving. So I print out the sum and I print out I. And we'll try compiling and running that. I'll just clear this. And we stare at this for a minute. I'm going to press Control-C. And you might have noticed it took a second before Control-C worked. You can stare at this for a minute and say, okay, the sum seems to be changing, but I is stuck at 1. Okay, so maybe I should go and look at the incrementation condition. And of course, that is where I put the error. So I'll save and compile and run this again. And now I still get this, I call this a debugging print statement. It's only there for my own purposes as a programmer. It's not really the point of the program. These debugging print statements still run at each step. At the beginning, before I've run the first iteration of the loop, it says the sum is 0 and I is 1. Then the sum is 1 and I is 2. And I can actually use this to verify that my calculation is correct. So I could step through this. I could also trace the code by hand, and this would help me make sure that my tracing is matching up with what's actually happening. But of course, if you wanted to hand something like this in and it said you can only have that last line of output, make sure you get rid of any other output before you hand it in. What I would recommend is don't delete the print statement, because maybe you might need it again later. Maybe something else breaks. Just put a comment in front of it. That will disable it for the purposes of the compiler, but you could always bring it back in if you need it later. And I don't mind. There's nothing wrong in this course with handing in code that has other bits of code commented out. That's fine. I mean, I do that myself. Don't worry about cleaning your code up for submission. Just make sure that it works in the virtual lab environment using the right compile command. And you can see there it is. I've commented out that print statement, and I'm getting back the answer. But I can always go back and bring the print statement in again if I notice a problem in the future.